So in our discussion today, I want to talk about valence electrons and how these valence electrons affect the formation of ions. There's a driving force among atoms to gain or lose electrons in order to reach a low energy stable state. And this stable state is obtained when an atom has an electron configuration of s2p6 at its outermost energy level. The atom is then said to have a full outer shell of electrons. For instance, argon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, whereas krypton's is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And that full outer shell, the 3s2, 3p6, and the 4s2, 4p6, even though it's separated by that 3d sublevel, that indicates that we have a full outer shell of electrons, s2p6. That's a very desirable state for an atom. Both of these elements belong to the noble gases on the periodic table. And noble gases, with the exception of helium, have this stable electron configuration of s2p6. So we often call this a noble gas configuration. So why is helium stable even though it doesn't have this s2p6 configuration? Well, if you remember, helium is simply a 1s2. But that 1s, that first energy level, all it has is that s sublevel with 2 electrons in it. That's the maximum it can have. So it does have a full outer shell for it. It just happens to be small. So it does have a full outer shell. Its outer shell just happens to be its first shell. So why is it virtually impossible to get a noble gas to react or bond with anything? There's no driving force. They already have that s2p6 configuration. So they have no driving force to want to bond with anything, um, and they have no desire to gain or lose any electrons to do that. Now, the valence electrons are the electrons that are present in that final sp configuration. They're very important because these are the ones that are involved when atoms bond together. So we give them a special name. We call them the valence electrons. Outermost energy level, S and P sublevels involved in bonding. And the number of valence electrons can be determined by simply noting the number of the group that the element is in. And if you have your periodic chart, you can look and see that barium is in group 2A. And since it is in group 2A, that's an indication that it has 2 valence electrons. Carbon's in group 4A, which is an indication that it has 4 valence electrons. And iodine over there in group 7A has 7 valence electrons. So all you have to do is to look at the group number at the top of the column and you can tell how many valence electrons there are. We have a special way of writing those valence electrons, and it's called the Lewis dot structure, sometimes called the electron dot structure. But again, it's just a method used to show the number of valence electrons. The maximum number of valence electrons, since it's s2p6, is 8. So there are 8 places where we're going to be able to put dots around this to get our Lewis dot structure. So they're numbered here, 1, 2, 3, 4, and then 5, 6, 7, and 8. So we can have a total of 8 dots around this. Sodium, if you look, it's in group 1A, so it has 1 valence electron. And the way we would represent its Lewis dot structure is to put Na, its symbol, and then over in the 1 position for the first electron, we would put a dot to show its number of valence electrons. Beryllium is in group 2A, so it has 2 valence electrons. So when we write the Lewis dot structure for beryllium, we would write a dot in the 1 position, and then you can see up here in the 2 position is where we would put the other dot. Nitrogen over in group 5A has 5 valence electrons, so we would write its structure with N in the middle, dot in the 1 position, 2, the 3's up at top, the 4's at the bottom, and 5 is back up at the top again, paired up. Oxygen, group 6A, has 6 valence electrons. So we're going to have oxygen, 1, 2, 3, 4, 5, and the 6th one is to the right. Finally, I have seen all kinds of weird things drawn for these. Argon has 8 valence electrons. And I have seen, don't write this down because it's wrong, I have seen people write a nice little pretty star like this. I've seen people write just 1, 2, 3, 4, 5, 6, 7, 8. I mean, it's ridiculous, not paired up or anything. Both of these are wrong, so don't write those. They are paired up around the structure. So with 8 valence electrons, we would have 1, 2, 3, 4, 5, 6, 7, and 8. So that's what it's supposed to look like. Helium is our exception because we're going to find out that one of the things you can do when you look at the Lewis dot structure, you can see places. This is just a little shortcut way of seeing how these can bond. You can note how many atoms can come in and bond with these elements by noting how many free electrons there are. For instance, sodium has 1 free electron that will form 1 bond. Beryllium has 2 free electrons, so that would form 2 bonds. Nitrogen has 3 free electrons, 3 bonds. Oxygen, 2 free, so 2 bonds that it can form. Helium, which has 2 valence electrons, watch it, it's an exception. It can't have 8 valence electrons. It may be in group 8A, but it only has 2 electrons. Kind of hard to have 8 valence electrons if it's only got 2 to begin with. So it only has 2 valence electrons, exception to the rule. Again, don't write this because it's incorrect. If we wrote those on either side, like the 1 and 2 position suggests, then it would indicate that we have 2 free electron, or 2 free spaces for something to come in and bond. Helium does not bond with anything. So in order to prevent that misconception, they simply write both of the electrons for helium over to the right. So keep that in mind when you're writing helium. It is an exception. So how can we do this whole forming ion things? Well, just as a little practice, number of valence electrons for barium in group 2A is 2. So it's going to look like this for its Lewis dot structure. Now, as far as the number of electrons gained and lost, electrons are going to be lost or gained in order to reach a stable S2P6 configuration. And we can either do that by losing the valence electrons completely or by gaining enough valence electrons to have 8. Our S2P6. Because if we lose the valence electrons, thinking about it, the row below it, the shell below it would be then full. So basically what we want to do is get to either 0 or 8, whichever is the easiest. So technically barium could lose these 2 that it has right here, or to gain up to 8 it would need to gain 6. We're always going to deal with the least number of electrons we can. So barium's going to lose 2 electrons rather than gain 6. When it loses 2 electrons, it loses 2 of those pesky little negative charges, so it's going to end up forming a positive 2 charge, and its ion symbol is going to look like this. It has lost electrons, so it's going to form an ion because it's no longer neutral. Ions have a charge. Sulfur has 6 valence electrons, so sulfur is going to look like this. So sulfur could either lose all 6 of those electrons to get down to 0 in its 0 valence electrons, or it could gain up to 8, which means it would need to gain 2. So if we've got the choice between gaining 2 or losing 6, we're going to gain the 2. We want to deal with as few electrons as possible. So this would end up with sulfur having a -2 charge. And the symbol would be S2 minus. We always put the number in the charge. Excuse me. Nitrogen has 5 valence electrons, so it's going to look like this. Not with sulfur, it's not. It's going to be nitrogen. 1, 2, 3, 4, and 5. So nitrogen could either gain 3 electrons to get up to 8 or lose all 5 that it has right now. Well, it's going to gain 3, the least number it has to mess with. When it gains electrons again, gains those pesky little negative charges, it's going to be a -3 charge. So its ion symbol is going to look like this. Potassium has 1 valence electron, so it will look like this. It could either gain 7 or lose the one it's got. It's going to lose that 1 electron. Once it loses a pesky negative electron, it's going to be positively charged. So notice that we don't put 1s in symbols or formulas, so it's just going to be K+. Carbon has 4 valence electrons, and it brings up kind of a situation here where we have these 4 valence electrons around it. It could lose 4 or gain 4, so which is it going to do? Well, both. Neither. Can share. There's a wide variety of things that carbon can do, which probably explains why it is the basis of all living organisms, the chemistry in all living organisms. So that carbon we're just going to say it can do both. It can lose the 4 electrons or it can gain the 4 electrons, which means that it could form a 4 plus or it could form a 4 minus. And actually that should have gone in the last column. I'm going to put a +4 charge or a -4 charge, and then C4 plus or C4 minus. Neon has 8 valence electrons, so it's going to look like this. Oh, that I'm not doing a very good job with my dots, so let's try that again. I'm just going to put them together at the same time. It doesn't look like this is going to cooperate very good with putting the dots exactly where I want them. So that's what neon should look like. Now think about it. Neon could wait. Does neon want to do anything? No, it does not. Number of electrons lost or gained, it already has 8. It's not going to do anything. It's not going to form a charge, and therefore it's not going to have an ion symbol. It's not applicable. Some people put Na0. I'll put that in parentheses over here, but that kind of indicates that it's an ion and it's not an ion. Helium. I had to show you helium because you'll mess up on that if you're not careful. Helium looks like this. Remember, it's an exception to the rule. And since it is a noble gas, now it's really easy to fall in the trap. Well, it's going to gain 6 or lose 2. No, it's not. Helium's an exception. It's not going to do anything. It's already stable. So it's going to have the same kind of situation as neon. So how do we name these ions, this ion nomenclature? Well, metals from groups 1A and 2A are named just as they are. Just name them, put ion on the end. Metals outside of groups 1A and 2A are named with a Roman numeral corresponding to their charge. So exceptions for naming them with this Roman numeral are the silver ion, cadmium, zinc, and aluminum. We don't have to put Roman numerals with those when we name those ions because we know their charge. We don't have to put anything with those. No Roman numerals are needed. These do not need Roman numerals. Negative ions are named by changing their ending to IDE. If the formula of an ion has 2 elements in it, it's a polyatomic ion, and you'll have to look it up. We'll talk about that in just a moment. If the name of it ends in ate or ite, it's a polyatomic ion. Look it up. So, examples. Br minus. Bromine is it's negative. So it's going to simply change the ending from bromine to bromide, and we tack the ending of ion on the end. Look for another negative one. We've got P3 minus here. P3 minus is simply going to be the phosphide ion. Mg2 plus, that Mg2 plus then, that is going to be with our positive ions. We're going to, if they're in groups 1A or 2A, name them as they are. Other ones get named with a Roman numeral, unless they're one of those 4 always true charges, which we'll talk about in a minute. Mg2 plus is in group 2A. Since it's in group 2A, remember in our rules, all we have to do is just name it magnesium ion. So when it comes to these positive ones, we can get a little confused fairly quickly if we don't really pay attention to where these are. So let's look at this periodic table really quickly. And I want to go ahead and label these charges. Remember we said groups 1A and 2A. If they are the ion, we don't have to say anything about them except just name them as they are. Well, that's because their charges are always +1 for group 1A and +2 for group 2A when they form these ions. Think about it, it makes sense. If you've got 1 valence electron, you're going to lose it like group 1A does. If you've got 2 valence electrons, you're going to lose it like group 2A does. Group 3A +3, we really don't know what these are. We sometimes call this the sea of unknown charge. So we often call that the sea of unknown charge. There are some islands in the middle of this sea. Now the sea kind of extends down through here. It really kind of goes all the way to the bottom here and kind of goes all the way to this staircase. So we've got this whole sea of unknown charge except for some islands, okay? The aluminum is one of our always trues that we mentioned on the previous page. Silver is as well, it's a +1. Zinc and cadmium are +2s, and those are little islands of always true charge in the midst of the sea of unknown charge. If they're in the sea of unknown charge, they need Roman numerals. So if they're in the sea of unknown charge, they need Roman numerals. Now, this +3 extends down to the staircase. There's a question mark for group 4A. Group 5A, again, extends down to the staircase, -3, -2, and these are common charges for oxygen's group, -1 for the halogens, and then 0 over here for the noble gases. They don't form ions. So those are simply some charges that you can have on your periodic table if you want to write these in that will kind of help you pinpoint this, because the one we just looked at was iron, and it's right here, and iron's in the sea of unknown charge. What does that mean? It means it needs a Roman numeral. So let's go back here and go back to iron. Since it's in the, again, in that sea of unknown charge, iron is going to need a Roman numeral. And that Roman numeral is simply whatever that numerical part of the charge is. So iron 3 ion is what we're going to name it. Lead, if you look back over here, you'll see that lead is in the sea of unknown charge over here. And it's not one of our islands of known charge, so we're going to have a Roman numeral with that. So going back to lead, we're going to use a numerical part of the charge. IV stands for 4. Remember, if you put a small number before a big number in the Roman numerical system, that means you subtract it. So 1 taken away from 5 is 4. So lead 4 ion. And silver, remember silver over here is one of our islands right here. It's an island of known charge. So those little islands of known charge don't need Roman numerals. So all we have to put for silver back here is simply silver ion. Now we come to these next ones, and if you'll notice the SO42- and the OH-, those have more than one atom in them. So what are those? Well, I'm going to skip over here a couple of pages to this page. This page is a list of polyatomic ions that I want you to be able to recognize. And if it has more than one atom in it, then you know that you're dealing with a polyatomic ion, so you need to look it up on this chart. Notice that all of these polyatomic ions, almost all of them end in ate or ite. That's your indication that it has oxygen in it. And you can usually tell what all is in the polyatomic ion based on its name. Hydrogen carbonate, for instance, has hydrogen, carbon, and oxygen, which you can see it does. Now, some of them don't make sense. Acetate, for instance. There's nothing in acetate that tells you that its name is C2H3O2 with a negative charge. But it does help us for most of them. Now, some of them don't end in ate or ite, and you have to watch for those. The 3 that we have to watch for on this list are cyanide, ammonium, and hydroxide, which is right here, right below cyanide. So those 3 don't end in ate or ite. So if you're not careful, you'll miss those when we're trying to write formulas or name compounds or something. So watch for those 3. But anytime you have any of the eights or ites or something that has more than one atom, this is the list you're going to go to. Now you are going to have a test over this eventually. There aren't very many that I expect you to know from memory. The most common ones are highlighted yellow on here. So you'll want to make sure that you know those and try to internalize those. Okay, so let's go back here to our list again. SO42-, as soon as we see that it has more than one atom in it, we're going to go to our polyatomic ion list. We're going to look for 2, so we won't have to keep flipping back and forth. We're going to look for SO42-, and we're going to look for OH-. So let's go back over here. SO42-, look for ones that have a 2- charge, and here's our sulfate. It's the sulfate ion. And then OH- is one we already mentioned is hydroxide. So those are the names of those 2 polyatomic ions. So let's go back and fill those in. So this is the sulfate ion, and this is the hydroxide ion. Now we can go the other direction too. If we're dealing with a name of an ion and we want to write the formula for it, that's where our periodic table that we just did comes in handy. Notice this is strontium, this is copper 2. Both of those are elements. Look at the last ones. This is carbonate. This is one of our polyatomic ions. So we're going to have to go to the list to find those, not the periodic. This one, not the periodic chart. The ammonium ion, that was one of the 3 we circled, again, on the polyatomic ion list that did not end in ate or ite, so we'll have to go to the list to find that one as well. But let's concentrate on strontium first. Strontium, let's go over here, and we can see that strontium is in group 2A. Well, what does that tell us? It tells us it has a +2 charge. So when we write the formula for it, this is a shortcut. When we write the formula for it, we're simply going to be able to write Sr with a 2+ charge. We don't have to go through what we just did in the table every single time we're dealing with one of these ions. The copper 2 ion, as soon as it has a Roman numeral, we're like high-fiving each other because we don't have to go to the periodic table. We can simply, since it has a Roman numeral, write that Roman numeral as the numerical part of the charge. Roman numerals are always positive, so it's going to be Cu with the 2 plus charge. And now for carbonate and ammonium, let's go to our chart real quick, to our list of polyatomic ions. And we see that carbonate is right, let's see, where's carbonate at? Here we go, right here. One of the ones that we need to memorize. Carbonate is CO3 with a 2 minus charge. Ammonium is one of the ones that we talked about earlier. Ammonium is NH4 with a positive charge. So going back to our list, let's fill in those last two real quick. Carbonate, CO3. Pay attention to how you're supposed to write those formulas, subscripts and superscripts. And then finally, the last one, NH4 with a positive 1 charge. Ones don't go in formulas, so it's just NH4 plus.